Hi, in the last video, we had gone over an experiment where we had connected a voltage source across gate and source terminals of MOSFET. Emitter was connected in series with voltage source across drain and source terminals. We concluded certain conditions of VDS and VGS at which MOSFET behaves in different ways like voltage controlled resistor and voltage controlled current source. I will give link to my previous videos in the I button in case you want to go over them. In this video, we will go over other possible connections which are possible with use of current source. Let's think of a case where we connect a current source at the drain to source side and voltage source at the gate to source side. Current from drain to source will be now fixed to ID amps as this current source will force flow of current through drain and source. Only unknown at the output side will be VDS, that is the voltage across drain and source. We know that output side is fully controlled by input side, that is gate to source side. From the IDS VDS plot, we can see that if we keep current IDS constant, which is indicated by horizontal line like this green line drawn here, for the given VGS, you can see that there is only one value of VDS where the green line meets the trace in IDS VDS characteristic. What we want to know is how much VDS will change if we give little nudge to input voltage VGS. This is similar to case in previous video where we calculated how much current IDS changes if we give nudge to input VGS. Change in output voltage delta VDS can be evaluated as ID times the change in the resistance from the drain to source of MOSFET. As IDS is constant, only component that changes will be change in Ron, that is absolute resistance of MOS as VGS changes. Gain will be the ratio of change in output voltage VDS to change in input voltage VGS. Let's evaluate change in output voltage delta VDS. Let's look at the graph and see if we get any hint. What do you see now are two traces taken out of IDS VDS graph. Now as we increase VGS, graph changes from bottom one to top one. Just for ease, these two graphs are corresponding to the exact change in VGS that we are giving to the MOSFET. Blue point marks the value of VGS, VDS and IDS before VGS changes. Now as we change VGS, the plot will shift from bottom one to top one. Eventually what will happen is, red point will become new steady state condition from blue point. You can see that red point has same IDS current as blue point and now it corresponds to different VGS trace. So everything is correct. Now we want to somehow predict the value of VDS after we gave nudge to the input VGS. As of now, in my previous video, we did not see any parameter which changes with both VGS and VDS at the same time, because that is exactly the case here as there is change in VGS and VDS at the same time once we give nudge to the input voltage. But can we use the same small signal parameters to predict how much will be the final change in VDS? Let's find out. As we see in the graph, transition from blue point to red point has not only changed VGS, that is the trace change, but also VDS is changed as well. What if we think about this process one step each? Let's think that change in VGS causes MOSFET current IDS to change, which we can calculate by value of GM. While we do that, from graph, we can see that we are moving vertically upwards. So VDS is still constant, which was the condition while measuring GM. But this change is not possible as the value of current through drain and source is fixed because of the current source that we had put there. So now, whatever IDS has changed should get cancelled or should go quote-unquote somewhere else. We will think about where the delta IDS has gone soon. Now, as we got to know that IDS cannot change, but as we have taken a step in VGS, now we are on the new top trace. So in this new case of VGS, we have to find same point where IDS is same as previous. As we already have done, red is the point on the new VGS trace where the current is same as before. So in all, first the IDS of MOSFET changes, then as it cannot change, it goes somewhere else or somehow gets cancelled. Since the final current through MOSFET will be same as initial current, VDS reduces to roll back the current to the original value. This is kind of a chain rule. First part of the chain is IDS increases, second part of the chain is that current is sucked in by someone and the current returns back to original value. Please pause, ponder and understand this enough. Now we can calculate first part of chain, which is change in IDS by our normal GM formula. So IDS will be nothing but GM times delta VGS, where delta VGS is the nudge that we gave. So what we looked at is change in IDS due to change in VGS. For the second part of the chain, we can see that on the top trace, which corresponds to the VGS after we nudge it, yellow is the temporary point from where the current returns back to red point. This change in current is purely due to change in VDS as VGS was constant for that trace. So what we are looking at now is change in VDS due to change in IDS. This is nothing but Rout as we know from the previous video, and also the condition while measuring Rout is constant VGS, which we have satisfied here. So if we want to calculate overall change, we will get delta VDS by delta IDS times delta IDS by delta VGS. This is nothing but GM times Rout. Now as seen from y-axis of the graph, delta IDS in both parts of the chain is same, so it can get cancelled. So we get delta VDS by delta VGS. This is nothing but voltage gain we wanted to calculate. Wow! We were able to evaluate seemingly complex relation between delta VDS and delta VGS by using the exact same small signal parameters from previous video. Delta VDS can now be easily calculated as GM times Rout times delta VGS. Now we know that values of Rout and GM change depending on the region of operation of MOSFET. Now let's see whether what we have calculated is correct. Drawn green circle represents the area which we played along in this graph. This area, as you can see, gets smaller and smaller if we had given smaller nudge to VGS. So if we had taken small enough steps in VGS, we should be pretty sure that the values of GM and Rout won't change because we are not changing the operating region abruptly. And in fact, we are playing in an area which is small part of the overall operating region of MOSFET. This is great, apart from the fact that we are yet to check where the delta IDS goes. We will see soon. Now the keen viewers might have noticed, as no matter what, IDS is not going to change. Then basically delta IDS is 0. Then why is GM not 0 and Rout not infinity? By their equations, it should actually be that way. But in fact, we just calculated voltage gain of the circuit with knowing GM and Rout values. Which of this is correct? Is GM really of some value or it is 0? You will get to know soon that too. Whatever we talked so far was valid when we gave a small change in VGS. But what about the absolute constant voltage that we need to provide? This figure will explain it better. Let's say we set VGS as 1 volt, which is let's say enough to turn on this transistor, and we set ID, which is external current source, equal to 1 microamp. Now from IDS VDS characteristics of MOS, we can find out VDS easily. We will also get to know the region of operation. Let's say that VDS comes out to be 2 volts from the plot. Now let's assume that value of GM times Rout for the given operating point comes out to be 10. So voltage gain is 10. What it means? Clearly it doesn't mean that if my input voltage VGS is 1 volt, I will get 10 volts at the output. It means that given the conditions of values that we had set, like VGS equals to 1 volt and IDS equals to 1 microamp, if I give small voltage nudge to VGS, let's say of 1 millivolt, you will be able to see that the change in the output VDS is 10 millivolts. This is what this gain is. As this is pretty similar to what we had when we had defined GM and Rout as small signal parameters because they were measured by nudging the required parameter. This gain can also be called as small signal gain. Also, we had provided some initial constant settings to the circuit to bring it to operate in some desired region, like we gave VGS equal to 1 volt and IDS equal to 1 microamp. This is called biasing. So we need to bias transistor in required operating region first before we use it as an amplifier. Now let's think about what all we are doing here. If you think, after we bias the MOS, operating region is fixed if we are giving small nudges to the input. This kind of ensures that operating region will not change. If so, then after biasing, the circuit can be thought in a totally different manner, like it gets all its small signal parameters at work. Let's call it a small signal model of MOSFET. This model of transistor will only include parameters which we call as small signal parameters. Now, how can we model it? Well, let's follow steps that we usually follow. After biasing, we generally start with nudging the input. So let's draw 3 points which indicate gate, drain and source. Now we are giving nudge from outside voltage source between gate and source terminal. Also we know that gate terminal doesn't draw any current from the input source, so there will be nothing connected from gate to source. Okay, input part is complete. Now we have two small signal parameters to put in, which are GM and Rout. How and where to put them? We know that we give nudge to the input VGS and that will translate to the change in current from drain to source. The value of this change will be GM times delta VGS. So this can be drawn as dependent current source whose value is GM times VGS. The current is flowing from drain to source, which can be known from our experiments. So the arrow of current source will be downwards, that is from drain to source. Okay, we are done with GM now. What about Rout? Where to put it? Well, basically Rout is just a resistor of value delta VDS by delta IDS. So the change in VDS will cause change in IDS. We just had modeled GM saying it will alter IDS. But we also have one more factor which alters IDS based on VDS, which is Rout. Hence overall current from drain to source will be current due to Rout plus current due to transconductance. So this resistor has to be connected parallel to GM. That's it. Our small signal model of MOSFET is complete. Remember that this model can only be used in cases where we are nudging the input. Also, and rather this is the most important point to note, this model has prerequisite, that is, MOS is biased in required region before we use this model. Let's try to use this model in our circuit that we were analyzing. Let's replace MOS with small signal model. The circuit will look something like this. As our model is small signal, outputs and inputs are also small signal. For example, referring to our previous example we took, now VGS will be of value 1 millivolt, not 1 volt. Now comes the trick. What will be the value of current source ID? We had set current to 1 microamp and we don't give any nudge to current source. So nudge is nothing but 0 microamps. So in our small signal model, current source becomes value of 0 microamps. It is as if it is not there, so we can remove it. Please pause and ponder on this thought. To continue, our output will be nothing but delta VDS, which is measured across drain and source in the small signal model. Here you go. Now our circuit is complete with small signal model of transistor. We know that this circuit is supposed to give gain of value GM times Rout. Let's see if we can visualize it here. We nudge the input. Because of this, current on the output side becomes GM times delta VGS. This current has no other way than to flow through Rout resistor. So it will flow through Rout and will generate voltage across it of value GM times delta VGS times Rout. You can see that this voltage is nothing but VDS. Wow, we just proved that the gain of this circuit is actually GM Rout. The gain will be actually negative. This can be seen because as the current will flow from bottom to top in the Rout, voltage generated on the drain will be less than the source. Keen viewers would have also noticed that this is where the delta IDS was flowing to. If you hadn't noticed it yet, no issues. Here is the simple figure. This was our external constant IDS. Now from small signal model, we know that there are two components at the drain side which are dependent current source of value GM times VGS and Rout resistance. Now as we know that the external current cannot change but GM times VGS current will still flow. We can see that the solution is still achievable if the GM times VGS current is flowing through Rout only. This way the external current also feels that it is pushing constant IDS, but internally one current is just bifurcated into another path. This is amazing. We saw initially that GM of this circuit becomes 0 as there is no change in IDS. But in fact there is change in IDS, just that it is not seen easily. This simple example helps us to understand the importance of using small signal model while analyzing any circuit. In the last video, we had analyzed case where we use voltage source at the input and output. In this video, we used current source at the output side. There are two more cases remaining. Moreover, this is only with source terminal taking as common between input and output. In short, there are many more interesting topics we will go through. For now, I will end this video here. Thanks for watching.